Hello everyone. Today we're going to discuss Euler, Herglotz, and the cotangent and sine function expansions. On the left we have Leonard Euler, and on the right we have the less well-known mathematician Gustav Herglotz. So the cotangent and sine product expansions. In 1748, Leonard Euler, who lived from 1707 to 1783, proved two remarkable identities. The first is the cotangent partial fraction expansion. Of course, it's not really a partial fraction expansion, because cotangent is not a rational function, but it has the flavor of a partial fraction expansion. You'll notice automatically that the right-hand side has poles at the integers, as does the cotangent function. Now for the product expansion of sine of pi x into a so-called infinite polynomial, if you'll temporarily permit the abuse of terminology. In the same way we write an infinite sum as a limit of partial sums, an infinite product is defined as the limit of partial products. Notice that the zeros of the product are the same as the zeros of sine of pi x. To orient ourselves, here's a graph of cotangent of pi x minus the cotangent expansion for relatively large n. As you can see, the singularities at the integers cancel, and the graph flattens to zero as n goes to infinity, so we actually have global pointwise convergence. Here's a graph of sine of pi x in high-degree partial product expansion. Evidently, the large oscillations of the approximating products get pushed away from zero as n becomes larger. Now for some history. This slide discusses Euler's original and brilliant discovery of the sine product. From a modern mathematical perspective, this argument is bonkers, but it's notable for its creativity and foresight. Euler's original point of view on the product was to use it to evaluate zeta of 2. So here goes. Sine of pi x is an infinite polynomial, which of course it isn't. So we factor sine of pi x using its zeros, which we can't do because sine isn't a polynomial. Then we rescale it to avoid divergence. But why this choice of rescaling? And write it as an infinite product expansion. This results in the expression on the right. To show that c equals pi, divide by x and take limits. This part at least is not controversial. While this argument is completely non-rigorous, it actually points the way to a rigorous proof. Euler just didn't have the foundations in place yet. His point of view foreshadows rigorous results appearing more than a century later, namely the Weierstrass and Hadamard factorization theorems from complex analysis. We mention all this for context, but we don't use this approach here. Euler's 1748 proof of the sine expansion is essentially complete by modern standards, but it doesn't have the fireworks of his 1736 argument. In that rigorous proof, he develops the sine expansion with a complex variable approach that we don't really discuss here. Then he deduces the cotangent expansion from it by logarithmic differentiation. Let x be a real number that's not an integer. What we're going to do is take the derivative of the logarithm of the absolute value of both sides of the expansion. In this upcoming formal derivation, we're not really justifying the series manipulations, at least for now. To speed our way, we just assume that everything we can do for finite sums and products, we can do for infinite products. Okay. Now, given that I have the product expansion, I'm going to use log properties to write the logarithm of the product as a sum of logarithms. Taking the derivative of both sides, doing so termwise on the right-hand side, we obtain this simple expansion here. Write the infinite sum as a limit of partial sums, and replace the fraction in the sum by its partial fraction decomposition. When combined with 1 over x and rewritten, we have the desired two-tailed sum. Now to introduce Herglotz's approach to the whole problem. Gustav Herglotz, who lived from 1881 to 1953, proved the cotangent expansion by what is now called the Herglotz trick. His proof uses minimal theory and algebra and is straightforward given a first undergraduate real analysis course. We're not going to use anything more sophisticated than basic results surrounding sequences and series of functions. As far as such results go, this argument is relatively new. The analyst Bachner was made aware of the argument by 1936, though it didn't appear in published form until 1954. In contrast to Euler, Herglotz derived the cotangent expansion, then derived the sine expansion by basically inverting logarithmic differentiation. Written rigorously at the same level of detail, Herglotz's proof is shorter than Euler's. So the broad steps of Herglotz's proof for the cotangent expansion are as follows. Step A, the routine part, shows that the error, that is, the difference between the cotangent function and the desired expansion, extends continuously and one periodically to R. An analyst who's trying to prove equality of the cotangent expansion from more or less first principles will be led pretty quickly to the conclusion of step A, but it's not so immediate how to proceed from here. This is where the Herglotz trick starts, with step B, where we verify that f satisfies this neat little functional equation and initial condition. Step C shows why we care about this functional equation in the first place. It turns out that any continuous function that satisfies this equation and initial condition must be the zero function. By parts A, B, and C, the error is zero on the reals, and we've proven the cotangent expansion. So the broad steps of Herglotz's proof for the cotangent expansion are as follows. Step A, the routine part, shows that the error, that is, the difference between the cotangent function and the desired expansion, extends continuously and one periodically to R. An analyst who's trying to prove equality of the cotangent expansion from more or less first principles will be led pretty quickly to the conclusion of step A, but it's not so immediate how to proceed from here. This is where the Herglotz trick starts, with step B, where we verify that f satisfies this neat little functional equation and initial condition. Step C shows why we care about this functional equation in the first place. It turns out that any continuous function that satisfies this equation and initial condition must be the zero function. By parts A, B, and C, the error is zero on the reals, and we've proven the cotangent expansion. To prove item 1, I just take the two-sided sum and write it as a sum of two one-sided sums. By re-indexing the first sum and combining fractions, the two sums are easily consolidated into a single sum with a simple summand. This argument is possible because the top and bottom bounds in G sub n are symmetric. For item 2, we need to show that the sequence of functions G sub n is uniformly convergent on bounded subsets of its domain. To this end, let V be a bounded subset of R minus C, and B be the supremum of the absolute values of x and v, and m and n be integers where b is less than or equal to m, which is less than n. To prove uniform convergence on V, it suffices to show that the sequence G sub n is uniformly Cauchy on V. That's not too bad. In particular, we'll show that the supremum of this difference goes to 0 as m and n go to infinity. By the definition of G sub n, we have this simple quantity, and the absolute value can be increased by taking the absolute value through the sum by the triangle inequality. The quantity can be further increased by taking n to infinity and replacing the absolute value of x by b. Finally, we have a bound with zero limit as m approaches infinity that is independent of x and v. We conclude that the sequence G sub n is uniformly Cauchy on V, and therefore uniformly convergent on V. For item 3, we see that G is continuous on R minus Z, since it is the uniform limit of continuous functions on any bounded subset of R minus Z. For item 4, to show that G is one periodic, we're going to show that this quantity on the left is 0. The right-hand side follows from the definition of G sub n, and since x is shifted by 1, I can perform an index shift in the first sum to match up the summand with that of the second sum. Now everything cancels except for the n plus first term in the first sum and the minus nth term in the second sum. The limit of this is clearly 0, so G is one periodic. Now for lemma 2, the second part of step 1, where we show continuity and one periodicity of the error function, whose domain has been expanded to include the integers. By lemma 1 and one periodicity of cotangent of pi x, f is one periodic on R and is continuous on R minus Z. And by one periodicity, if we can show that f is continuous at 0, then we know that f is continuous at all the integers. Since the limit as x approaches 0 of the sum in g is 0, I have this simple expression for the limit as x approaches 0 of f of x, which can be evaluated with two applications of L'Hopital's rule. It's time to get on with the proper start of the Herglotz trick. From here onward, let I be the closed unit interval. We have lemma 3, which states that the error function, which is piecewise expanded, satisfies a functional equation on I. We'll begin by showing that this functional equation is satisfied on the open interval from 0 to 1. That cotangent of pi x satisfies it follows from the cotangent double angle formula. The details are here for you to pause and verify at your leisure. Now we're going to verify that g satisfies the functional equation on the open interval from 0 to 1. By the definition of g in the teensy bit of algebra, the following holds. The first term in the limit is simply the sum of reciprocals of x plus even integers, and the second term is the sum of reciprocals of x plus odd integers. These two terms can easily be consolidated into a single two-tailed sum, which can then be related to the definition of g sub 2n plus 1. Taking the limit shows that g does indeed satisfy the functional equation. By equations 7 and 8, f satisfies the functional equation on the open interval from 0 to 1. But f is continuous on I, so it satisfies the functional equation on this interval as well. Okay, the payoff is right around the corner. Lemma 4, Herglotz's final ingredient, shows that the only continuous solution to the functional equation on I with f of 0 equals 0 is the 0 function. To prove the lemma, let m be the max of the absolute value of f on I, which exists since I is compact. Furthermore, let x naught be a point in I at which this maximum is obtained. This first equality follows from the definition of m. The ensuing inequality follows from the triangle inequality and the fact that f satisfies the functional equation. The next two inequalities follow from the definition of m. Taking note of the highlighted inequalities, we see that the maximum absolute value of f is also obtained at x naught over 2. Looking at the highlighted equations, we observe that we can iterate this argument and derive that the maximum absolute value of f is obtained at x naught over 2 to the n for any non-negative integer n. Since f is continuous and f of 0 is 0, we can take the limit of this equality as n approaches infinity and conclude that m is equal to 0. Therefore, f is 0 on I, and the lemma is proven. Finally, by lemmas 2 and 3, the extended error function satisfies the hypotheses of lemma 4, so f is 0 on I. But f is one periodic, so f is 0 on R, which at last gives the cotangent expansion. Herglotz's argument is startlingly clever, because nothing was required beyond basic first-year undergraduate real analysis. Now that the cotangent expansion is established, we're going to outline how the sine expansion follows from it. The idea is basically to reverse logarithmic differentiation, though the devil is in the details, and a rigorous implementation is somewhat delicate. Step D. Basically, undo the differentiation part of logarithmic differentiation. For each integer n, integrate both sides of the rearranged cotangent expansion, passing the integral through the sum, to obtain an antiderivative that is constant on each interval from n to n plus 1. The reason why, at this point, that we can only say that the antiderivative is piecewise constant is this. The sum is discontinuous at each integer, so to apply the fundamental theorem of calculus, no interval of integration can contain an integer. Step E. Will show that the piecewise constant antiderivative extends to a constant function on the entire set of real numbers. Step F. Exponentiate the constant antiderivative to get an absolute value form of the sine product expansion. This exponentiation undoes the logarithm in the logarithmic differentiation. Step G. Justify the removal of the absolute values to deduce the sine expansion. Here we go with step B. Given an integer n and z, I'm going to let a and b be in the interval from n to n plus 1 and integrate both sides of the rearranged cotangent expansion on the closed interval ab. Lemma 1 states that I can write the two-tailed sum in the integrand as a uniformly convergent one-tailed infinite sum on the interval ab. With this in mind, we can pass the integral through the sum. We obtain h of b minus h of a is 0, where h of x is the antiderivative defined below. H of x is therefore piecewise continuous on each open interval from n to n plus 1. Furthermore, call the value of h of x on this interval c sub n. Now we're going to show that the locally constant antiderivative h of x is actually constant on the entire real line. Let n be positive and x be in the union of the open intervals from n minus 1 to n and from n to n plus 1. We're going to show the antiderivative is globally constant by showing that the limit of h of x exists as x approaches n. Notice the highlighted term is the nth term of the sum, rewritten with the product rule for logarithms, that I have peeled off from the main sum. This modified sum is now continuous at x equals n. Consolidation of the middle two logarithmic terms on the right-hand side allows us to take the limit as x approaches n. The particular value of the limit is not important. What matters is the fact that the limit exists in the first place. Therefore, we can conclude that h of x extends continuously on r minus 0 to a single constant. And it also extends continuously to 0 by the small angle approximation, which additionally allows us to find the value of the now global constant c0. Therefore, the highlighted equality holds on r minus z. For step F, I'm going to exponentiate the prior highlighted equality and use basic properties of logs and exponentials. A tiny bit of algebra yields the following. Rewrite this infinite sum as a limit of partial sums. Then use that a sum of finitely many logarithms is the logarithm of the corresponding finite product. Then use continuity of the exponential function. And finally, that the exponential and logarithmic function are inverses of each other. The last big step is to remove the absolute values in the previous equation. Here we still consider x to be a positive non-integer. We can write sine of pi of x using its absolute value by accounting for the sign changes as x crosses over integer values. This gives sine of pi x is minus 1 to the floor of x times its absolute value. Then we use equation 12. We now break the infinite product for the absolute value into two pieces. The first where k is less than or equal to the floor of x, and the other where k is greater than or equal to the floor of x plus 1. In the first product, the absolute value flips the sign of 1 minus x squared over k squared, which is negative, and is redundant in the second product. Now we factor out floor of x many copies of minus 1 from the first product, then the simplification becomes evident. We can merge the two products together with no absolute values at all. This gives us the sign product whenever x is a positive non-integer. Both sides of the equation above are odd, and are trivially satisfied when x is an integer, so the domain may be extended to R, giving the full sign expansion. Phew, that does it. Thank you very much for watching this video. I appreciate those of you who are willing to stick it out to the end. It was a lot of fun to make. Please let me know what you think in the comments, and if there is any particular topic you would like me to talk about in the future, let me know. Have a great day.